Thank you. My name is Dae-Sik Lee. It's my pleasure to be here to give my talk today. Today, I will talk the lung cancer early screen sensor. I want to talk two topics. One is first version system, second version system. I want to show the two. We made two systems, and we did the clinical testing our system in the hospital. So I want to show the result, and finally I want to show briefly our future research directions. My interest is from basic research to the industrialization. In our labs, several kind of prototype of device, the sensor devices. In my research experience, I established two startup companies. Two companies listed in Korean Kosdaq, like America, and Nasdaq, and so I have a chance to patent transfer to the company and trying the commercialization. So I'm very interested in the industrialization of the technology. Today, I want to talk of the electron node sensor, especially the application to the lung cancer diagnosis. As you know, lung cancer is the second most popular cancer among all types of cancers. But especially in case of lung cancer, is a very lethal form of the cancer. So it's very important to early detect and the proper treatment at the early stages to reduce the mortality rate. The personalized now have attention from the society. World Economic Forum set the breast sensors as one of the 10 emerging technology in 2021, and that the market size also increased. The average growth rate is 15%. So now there's some prototypes, as you know, is showing in the market. The basic sensing target is VOCs of volatile organic compound. Is this is emitted from the skin or urine and the breath. I am interested in breath. To analyze the breath component, usually the analytic instrument like GCMS, BTRMS, and another one is it shows the list and the abundance of the VOCs. The next is now is popular one is the biosensor. The antibody and the antigen reaction is the key and the rock, very high sensitivities. Now I want to this I express in the big fishes because it's very good the sensitivity and the specificity. But nowadays, the electron nodes is systems using the sensor rays give and the AI overcome the big fishes. So I'm interested in this area. This graph shows the component of our breath, exhaled breaths. Usually it's nitrogen, oxygen, and carbon dioxide, and humidity. But under the 1 ppm levels, it's most of disease-related VOCs located here. So and in this figure shows in the ppm levels, acetone and the carbon monoxide and the methane, but under the sub ppb and ranges, so many VOCs, like formaldehyde. To analyze this component, shift mass and the beta top mass parts, this instrument is utilized usually a non-invasive method, but it's expensive and very bulky systems, as you know. As a point of sensing materials, there are big issues in the for medical application. Basically, the sensitivity. I showed before slide. It covered the sub ppb concentration. In point of view of selectivity, it needed more selectivity to the level of the biosensing levels and the reproducibility. It's a very important thing. It's sustainable for the more than several months. So you know the metal oxide sensors and the ionic conductor graphene polymers published so many journal papers, but that had the pro and cons. And especially metal oxide sensor, high the response is high, speed is fast, reversibility good, but the sensitivity is limited to detect the sub ppm. So it systematically it can covered by pre-concentrators. To enhance the selectivity is U-material and the sensor arrays give a pattern like a fingerprint. The pattern recognition by the AI algorithms. So reproducibility can be the detection of a fingerprint. It is the artificial intelligence AI give the big chance to put the reproducibility. This is a roadmap, the industrialization roadmap from the NIH. He is a director in NIH. I borrowed the slide from these pictures that show the fundamental research, from the fundamental research to the regulation acceptance. The worst procedure is to be mastered to be a medical device. Especially the electron node technology is located in the nearly to the pre-clinic development, clinic development. So if after 5 or 10 years later, the technology can be reached to this regulatory acceptance. Actually, we did this research topic for more than 10 years. We fabricated like these prototypes, and at that time, 7 metal semiconductor metal oxide sensors, and that case, 2015, and at that time we showed the accuracy 75%. Lung cancer 37, health control 98 means. At that time, we did clinical testing in the Seoul National University Hospital. And at that time, we published in Sensor and Actually, and we have, fortunately, we are broadcasting in KBS in Korea. It's like ABC in US. This slide shows our approaching strategy. In the lung cancer patient, breast include like this VOC as a biomarkers. Concentration level is sub ppm levels. Very different kind of chemical reactions with the sensors. Typical sensors make excellent sensing material, but it's very, so using the discrete sensors is very challenging. So we trying to multi-modal sensors. It's in on the systematic approaches, multi-dimensional signal and the AI learning, data augmentation, and high selectivity. And we are in the systematic approach needed the pre-concentrated module and yes, on the signal processing, reducing the interference. So we made, based on this assumption, we made two systems. We searching the biomarkers, the human disease, and the exhaled breast gases, the paper studies. In the lung cancer is, you know, some toluene and dodecaine and several POCs is appeared. Comparing to the health controls, colon cancer, breast cancer, prostate cancer, diabetes mellitus has a different kind of, they have a unique, their own biomarkers reported. But you know, I want to confirm it is right or not. So we did in our own the Korean papers for the lung cancer screening. You simple test using the sample collection and the tank tubes and the pump and the GCMS instrument, and we are made a protocol like this, and for this searching for the biomarkers. This table shows that this one's healthy ones. This is lung cancer, this gastric cancers. The type of BOC is humans. You can see in this, there are difference between the disease. So we found some candidate as biomarkers, and for lung cancer, ethyl butyrate, benzene, decarbon, xylene exit, something like that. You know, but the number is under the 100 bands, but we did more research in the future. We are planning, but among our research results, we can say there are the difference in their biomarkers can classify the health control and the cancer patient and the cancer types, lung cancer or gastric cancers. But basically, we are designed this sensor systems. It's based sample collection and the sensing and the signal processing and the disease diagnosis and based on deep learning. We are collected the sampling like this, and we made sensor arrays and generated the patterns using sensor materials. We are doing research on this metal oxide sensor, carbon nanowire sensors, and the peptide sensor, metal organic framework sensors, and the bacteriophage sensors. And we did apply to the AI deep learning algorithms, and then the health and the patient. Yeah. This is the first version result. We made like this systems. We consist of semiconductor metal oxide sensors and the electrochemical sensor and the PID gas sensors, and we did the clinical data collection from the university hospitals, and we designed the deep learning algorithm with the data pre-processing, like using the CNN algorithms, and we got the classification result. This slide shows our sensors systems. The first part is electrochemical ones, and this is metal oxide, and this PID, photoionization detectors, and three kinds of gas sensors. We got the breath samples using the tunnel bags and concentrated in the carbon tubes, and then applied to the sample to the chamber with the different kind of sensors. Yeah, at the first version, we used the commercialized sensors from the Japan, from Korea, and yeah. But at that time, as I mentioned before, the reproducibility is very key point in our system. So at first time, we obtained an reproducibility of the sensors performance. We selected the commercialized sensors, and this is the data critical data collection. It is the doctor designed this protocols. The lung cancer at that time, 90 men, and the health control 74 persons, men and the females. The histologic, and we especially target the early screening. So at that time, the populations in the stage 1 and 2nd, and it's about 70%. So we did the collection, the sampling before the operation, physical operation. So we got the size of the tumor tissues, but not appear here. So using the sample data, we got the sensor signal patterns like this one. This one is from the health control, from the semiconductor metal oxide sensor. This is also lung cancer from the semiconductor metal oxide sensors. There are the difference in the patterns. So from the PID and the electrochemical ones to the lung cancer ones. They show also difference the patterns. We using the pattern, we applied this pattern to the deep learning algorithms. So this is our design of the AI algorithm using the CNN, convolutional neural network. It is very popular in the image processing part, and we made one-dimensional CNNs, and the clinical data set is like this. Input data is we normalize the sensor responser and like this, and then time responser to map. We tried the input data, the responser to covers as image data. One convolutional layers, three dense layers like this, and Lulu activation function and the batch normalization. The output result is two classification: healthy control and the lung cancer. This the result shows we totally more than 100 samples using 10% of a total data set as affiliation data. After learning, and we applied the validation data, the prediction rate 88%, especially to the lung cancer only, and 100%. And it's predicted in this case is total data set is to the 96%. Validation and the test data is not included in this tester. It's 90%. So it shows very high accurate. So we want to check our approach to the using the multimodal sensor rate. In case of using only metal semiconductor metal oxide, it shows 97%, and to the training and the test data is 80%. But in case of multimodal SMO sensor, EC and the PID, in that case is to the training data is 100%, and its testing data is 90%. So in using the multimodal approach is comparing to the only semiconductor metal oxide, the accuracy increased more than 10%. So multimodal sensor array approach is working. And the second one is using you compare the difference the performance of among the AI algorithm. We consider the multi-layer perceptron and the convolutional neural network, and you can see in the tables the MLP, the 8%, and the CNN in case of 90%. So the proper selection of AI is improve the performance. And so using the ROC covers it also shows the CNN is working well comparing to the MLPs. We compared the previous result to the applying to the lung cancers. This is our works. Usually they're using the second AI algorithm. In this case is show LDA in the PUSI and SVM and SGR, KPC and the X boost, and we are only CNN. We showed the more good performance comparing to other research groups. So multimodal sensor and CNN algorithm is without pretreatment working well. So in this experiment, we basically we design and fabricated the breast analyzer with the multimodal gas sensors, and early screening and the convolutional neural network is working well in here, and demonstrated the computer metrics and the ROC curves, and this is the result. This is result was published in this year in early. So the next version is we are in now is preparing the publish for. In this case, we are including more sensors like CNW and bacteriophagy and organic frames, the peptide sensors, and we increase the sensor performance like this. So in material is included more included, and AI algorithm also enhanced. We first developed the metal organic frameworks, and MOF's material is known as high surface area and durability, and due to the porous nature of the metal materials, we control the physical performance and the chemical performance, and we developed the arrays based on these morphed materials. So we got the high sensitivity and high selectivity to the acetone and the toluene, isopropyl, and the 2-methylpentane. It's a biomarkers to the lung cancers. I mentioned before, so good. It's patterns for the classification. We got the like patterns, and we applied it to the types and the concentration. Also, we also developed the bioreceptor materials. We basically made the carbon nanowells and the silicon wafers with the microelectrode arrays, and the packaging and this like this. And we bioreceptor was developed as with mass production It also published journals several times, but in this case, we are put the bioreceptors on the carbon nanowires like this, and we uh, investigate the sensitivity like this. This shows the CNW gas sensors to the IPA and to the acetone. It shows the ROD value is 40 ppb levels. So it shows very high sensitivities. It's another one, the bioreceptor and the CNW. It is more you know, exclusively sensitivity to the 70 ppt to the pyronic acid and butyric acid to the 1.8 ppb levels. So good responsibility and specificity. We also designed the CNN AI algorithms. In this case, we efficacy among the MLP, RNN, and CNN, and comparing the performance. And we are weighing based on the sensor output. This is the sensor arrays made of patterns, and this is AI structure, and this is the pattern and the recognition. We are in this case we are applied the hierarchical clustering models to maximize the learning infections. We are second version. We are expanded the target disease to the lung cancer to the gastric cancers. This shows the second version of the systems. This shows that the sensor response. The sensor response was more fasterly workings, and this is the MIP sensor arrays, and it's a GUI. And it shows that the result. We are IRB approval from the Relational Hospital. To the lung cancer, we 93%, and the normal control 72. The stage is total covering the 90%, 1 and 2 stage levels. The gastric cancer is in case the patient 100 persons and the health control 72%. Stage 1 to 3 is covering 93%. We got to the lung cancer. We also put the result 97%. To the gastric cancer is 95%. This is the summary. We are the personalized second. It includes new materials, MIP and the CNW bioreceptor. We applied the lung cancer, gastric cancer, and the good performance, 97 and 95%. We want to future research. We want to apply this to the risk-based monitoring, the personal medicines. So we want to expect the future good result. Thank you for your kind